Hi y'all. Today's lecture is about limits. We're going to be looking at the notation of limits and how to find limits given a graph. So the first thing I wanted to go over is just when you see f of c, so f of 2 or f of a or g of 2 or g of a, remember that means that when you plug in c, right, when you plug in c into f, what do you actually get? Where is the value sitting when you plug in c? Okay, so I'm going to write how the function is defined at x equals c. But it literally means where is the value? Where is the dot sitting for that point along the graph? Okay? Maybe the f of c is undefined because there is no value when you plug in c into the function. Okay? Just want to remind you that f of c, where the function or how the function is defined at c, it's a totally different conversation than a limit question. Okay? Let's look at the formal definition of a limit. And the great thing is you are not responsible for this formal definition of a limit in this class. If you take college calculus, I'm sure your college professor will hold you accountable and you will learn all the details about delta and epsilon. But here in our course we're going to briefly see the definition, see how it works, and then apply that. Okay? But you are not responsible for the delta epsilon. Okay? So I'll read the definition because I'm sure you can't see it. The limit of f of x as x approaches a will equal L, the limit. Okay, if and only if, for any epsilon greater than 0, there is some delta, also greater than 0, such that the absolute value of x minus a is less than delta, then the absolute value of f of x minus L has to be less than epsilon. Okay, so what does all that mean? Basically, y'all, it means that as we get closer and closer to our x value, okay, and we'll call this value delta that we're moving away from our x value, we need to be getting closer and closer to some y value, which we call our limit, and the distance away we'll call epsilon. Okay? So basically what this is saying is in order for there to be a limit in a graph, the value that we approach from the left has to equal the value that we approach from the right. Okay? But it doesn't matter what's actually happening right at the value. It matters what's happening as you get closer and closer to that value. Okay? So this animation is a great description. Oops, hold on. There we go. Okay, so if you can imagine the blue, as the blue is getting smaller and smaller, so as we get closer and closer to A, there will be a limit as long as this purple, we're getting closer and closer to the same value over here along our Y. Okay, so as this delta is getting smaller, you can see here that the purple, the epsilon is also getting smaller. Okay, and as we get closer and closer, the outputs are also getting closer and closer. This is a linear function. Linear functions will indeed have limits. Okay, let's look at another example. Because these are kind of the more interesting problems is when we have a piecewise function. Okay? Remember, piecewise function is a bunch of functions that come together and we're just looking at certain pieces of those different functions. Okay, so this is a classic case here at A. We have a linear function coming in from the left, and as we approach from the right, we have this parabolic function. Okay? So if we look, we'll be learning this definition or the notation today. If you have something where it says as x approaches A and then there's a little minus after it, that will mean the limit from the left. Okay? So the limit from the left, as you approach A from the left, what value we're getting closer and closer to. So there would be that animation. If they ask you from the limit from the left, you see where are you getting closer and closer to as you approach A from the left. Okay? And the value to, or the answer to limit problems are always y values. So here the limit from the left, we'd be getting closer and closer to 3. Okay? So you're tracing along the curve, or in this case along the line, as you get closer and closer to A from the left would be 3. If we look at the limit as we get closer and closer to A from the right, we would be following this parabola. Right? As we get closer and closer from the right, we'd be getting closer and closer to this value, 4. Okay? So this is part of what we're going to be looking at today. We will say that a function only has a limit at x equals A if the left-hand limit equals the right-hand limit. Okay? In this case, we would say this function does not have a limit at x equals A. The limit from the left equaled 3 and the limit from the right equaled 4. Since those values are not equivalent, we would say there would be the limit does not exist. Okay? So there's some good graphics on that. Let's move to the definitions real quick. Okay? All of these blanks you're not filling in those blanks. I just want you to remember that the answer to limit problems, right, whatever sits here, are always going to be outputs. They're going to be y values. Okay? They're not x values. They're y values. So all of these are always going to be y values. Okay, the answers to limit problems. And then this is just the definitions, okay? The limit of f of x as x approaches c will equal some value, right? And the way we say that out loud is the limit of f of x as x approaches c. Okay. Again, hopefully you can see on your paper here the difference. This says as x approaches c, and there's a little plus. The little plus means you're approaching from the right. And then the little minus after the c means you're approaching c from the left. And I was always confused why students were confused on this. Let's reset this. Until a student last year mentioned, well, it's confusing for me because if you're traveling, if here's A and you're traveling from the left, your finger is actually moving to the right, right? And if you're approaching A from the right, your finger is actually moving left. So if that helps you, you know, when you see the movement, the little minus means you're coming from the left, and the little plus means you're coming from the right. But your fingers will actually travel in the opposite direction. Okay? So make sure you're clear on that. These two guys, if you see the little infinity, the limit as x approaches infinity, okay? That means that x is increasing without bound. X is getting bigger and bigger and bigger. X equals 10, x equals 20, x equals 100, 1,000, 1,000,000. What's happening? Okay? And as x approaches negative infinity is as x decreases without bound. So as x gets smaller and smaller and smaller. Okay? And so when you see those kinds of things, if you say it out loud, I'd want you to say these phrases, not as x approaches infinity. Okay, as x increases without bound, as x decreases without bound. Okay. All right, so here's these three answers all mean the same thing. Okay, the limit as we approach c equals, and we see a positive infinity here, a negative infinity, and a dne. Okay, so let's get a little help from the internet here, and let's remind ourselves what this is talking about.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh God, he looks so cute. Okay, focus, David. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mad Lakes.
All right, so finally, you actually can't do that problem quite yet. We haven't learned the math to do that problem, but eventually in this class you will know the math, so you'll do that problem. But the limit does not exist, all right? So if you ever get an answer, so infinity is the idea that the values are increasing without bound forever, okay, or negative infinity, decreasing without bound forever, or DNE stands for does not exist, okay? So the limit does not exist, and so this is the safe answer, is to say DNE, okay? Because positive and negative infinity are actually specific answers. They're specific ideas of increasing and decreasing without bound, but does not exist covers all of those situations. So always a good guess on a limit problem if you don't know what to guess. Does not exist would be a good answer, especially to recognize Mean Girls, classic movie. All right, a few other things. Whoa, that was weird. I mentioned it earlier. In order for a limit to exist, the limit from the left has to equal the limit from the right. Okay, so the limit from the left has to equal the limit from the right in order for there to be a limit at the actual value. If they equal different values, the limit does not exist. Okay. Again, one last time, the answer to a limit problem will always be a blank value. Pause, write it in, see what you think. The correct answer on that is a y value, right? An output, a dependent variable. You're never answering an x value. The x value is where you're approaching. Okay, that will be written in the problem. So I try to make these examples big enough so you can actually see. And you're just going to be basically writing in what value you're getting closer and closer to. Okay? You're going to be putting your fingers on the graph and actually, approaching from the left, approaching from the right. If you call me over and ask me about limit problems, I will often say, okay, get those fingers out and let me see you moving as you get closer and closer. To really experience it. All right, so this first guy is saying limit as we approach 1 from the left. Okay, so here's 1. As we get closer and closer to 1 from the left, I'm getting closer and closer to 1. Okay, so the answer there would be 1. As I approach 1 from the right, so here's 1, and here's the graph along from the right, I'd be getting closer and closer to 2. Okay, so the limit from the left equals 1, and the limit from the right equals 2. So is there a limit as we approach 1? So as I get closer and closer to 1, from the left I was getting closer to 1, and at 2 I was at 2, or sorry, at 1 I was at 2, so there would be no limit here. The limit as we approach 1 would not exist, does not exist. Okay? Now here's that separate question. This is not a limit question, right? What does f of 1 equal? So f of 1, remember, is asking you, when you plug in 1 into this function, what do you get? Right? When you plug in 1 into this function, what do you get? And there's the key point of this problem is a closed circle compared to an open circle. F of 1 equals 2 in this problem. That's where the actual dot is sitting, right? F of 1 that equals 1, or sorry, when you plug in 1 and you don't get 1, that's showing you that you're not getting 1. You have an open circle there. But it's saying that if you plugged in 0.9999, you would get, 0.9999. You're getting really, really close to 1. But at 1, you jump up to 2. So if we said what f of 1 was, that would equal 2. Okay. If you want to pause and give these your best shot, see if you can figure out how these work, that would be great. Test yourself. All right, 1 from the left. Again, we happen to be evaluating at 1. As I look at this graph, 1 from the left, I'd be getting closer and closer to -1. So that would be -1. As I approach 1 from the right, looks like I'm getting closer and closer to +1. Okay. Therefore, the limit as I approach 1, since the limit from the left does not equal the limit from the right, there is no limit. The limit does not exist. And then f of 1 in this case, it looks like f of 1, I'd plug it in, that's open, but there's my actual dot. It looks like it equals 0. Okay. Next few problems, as we approach, looks like 1 from the left, getting closer and closer to 1. 1 from the right, getting closer and closer to 1. So, because the limit from the left equals the limit from the right, then there will be a limit at 1. It will actually equal 1. Okay? So notice that we have an open circle here. When I ask you what f of 1 equals, you're going to say, does not exist. There is no value for this graph when you plug in 1. Okay, so it's okay for the value at 1 to not exist, and you can still have a limit. Okay, so you have to be okay with that and learn to accept that. Okay, really similar example number 4. The limit from the left as we approach 1 is still 1. The limit as we approach 1 from the right is still 1. Therefore, since the limit from the left equals the limit from the right, it's still going to be the exact same value. Now this time, f of 1, we still had that open circle here, but now we had a definition. When we plug in 1, we got -2. Okay, so notice that there will be a limit whether there was a value defined somewhere else or there was no value defined somewhere else. Okay. Does not stop us from having a limit. All right, example number 5. We're looking at just a nice, looks like a semicircle, right? We're approaching 0 from the left, so 0 from the left. We're getting closer and closer to, looks like 1. And again, this is just, we're assuming a lot here in these graphs that it was like perfectly lined up to all those values, and that's totally safe for tonight. Okay. As we approach 0 from the right, we're also getting closer and closer to 1. So therefore, the limit as we approach 0 would just be 1. And f of 0 also was 1, right? We'll look at, kind of those last 3 examples when we look at our definition of continuity. Okay. All right, example number 6. As we approach 2, okay, it looks like there was an asymptote here at 2. So as we approach 2 from the left, so I'm getting closer and closer to 2, closer and closer to 2, it looks like I am going up and up and up forever and ever and ever. Okay, 2 acceptable answers. You can write the cute little infinity sign, right? The limit as I approach 2 from the left is increasing without bound. Or you can say the limit does not exist, DNE. Either of those are fine because infinity, y'all, is really just the idea of a number. It's this idea that keeps on growing. It's not an actual number. Okay? And the only time you actually get an answer for a limit is if you're getting closer and closer to one single value. Okay? So either of those answers would be fine. On a multiple choice test or on the AP test, only one of those answers could be sitting there. They could not have both of those answers because they would both be correct. Okay? Limit as we approach 2 from the right. So now we're getting closer and closer to 2 from the right, going down in this case. So that would be a negative infinity. I am decreasing forever and ever and ever. So negative infinity or does not exist. Either one would be fine. Okay. So because the limit from the left was positive infinity and the limit from the right was negative infinity, the only acceptable answer for the limit as we approach 2 is just does not exist. Hopefully you can see we're clearly not going in the same direction. Our fingers are clearly not getting closer and closer together. Therefore, the limit does not exist. And here, f of 2, if you try and plug in 2, you're not getting a value. So all of these did not exist. Okay, we got a few more here. Example number 7, we're looking again as we approach -2 from the left. So -2 from the left, we're getting closer and closer to this asymptote, but never actually reaching it. Again, we would be increasing without bound. So positive infinity, or does not exist. Okay. -2 from the right, again, increasing without bound. So positive infinity, or does not exist. Okay. Now, because they were both increasing without bound, that would be an acceptable answer. The limit as we approach -2 could totally be positive infinity. As opposed to the last problem, notice the only answer I wrote was does not exist, because they weren't heading in the same direction. But in this case, they're both heading in the same direction, so positive infinity would work, or does not exist. Okay. And then f of -2, again here when I plug in -2, I'm not getting a value, so f of -2 is undefined or does not exist is fine. Okay. Example number 8, again we have an asymptote. The only difference here is that we have an actual value. When we plug in -2, we get 0. So these would be exactly the same as this guy, except f of -2 would be 0. All right, our last page is all about infinity, positive infinity and negative infinity. So again, this idea of infinity is increasing without bound or decreasing without bound for negative infinity. Okay, we will have a whole other video just on comparing growth rates, but just to give you the idea of what's happening, if you would pause and read through that at some point. Okay, and I like this. Stu Schwartz, by the way, whose worksheets I like to borrow sometimes, outlines this really nicely. There's basically 5 different situations that can occur if you're approaching infinity or negative infinity. Okay, parabola here on example number 9 is a classic example, right? If you keep plugging in bigger and bigger values for x, you're going to keep getting bigger and bigger values for y. Okay, so in this case, and this is also the same if we go to the negative side, right? You plug in smaller values, you're going to keep on getting bigger and bigger and bigger. Okay, so in this case, the limit as we approach negative infinity is also going to equal infinity, right? As we get smaller and smaller, these values over here, we're still going to be getting bigger and bigger values. Okay, and up here, we're also talking about the limit as we approached positive infinity was also going to positive infinity. Okay. Example number 10 here, we talk about the limit as we approach infinity going to negative infinity. Right? As I get bigger and bigger for x, these values would be continuing to decrease forever and ever and ever. How about as we approach negative infinity? So as we approach negative infinity, as these values were getting smaller and smaller, hopefully you can see that these values would just be getting bigger and bigger and bigger. So that would be a positive infinity. And again, on both of these, you can always put or does not exist. Totally fine. Okay? They are equivalent answers. Here we go. Example number 11. So in this case, we have where the limit as x approaches infinity is an actual value. So if you have a horizontal asymptote and your curve is getting closer and closer, like for instance in this case, we're getting closer and closer to what looks like 1, right? As x approaches positive infinity, it looks like we're getting closer and closer to 1. As x approaches negative infinity, it looks like we're getting closer and closer to -1. Okay. So the idea is with infinity, you're just going to go on forever in the positive direction, the negative direction, and see what you're getting closer and closer to. Okay. Last but not least here, the last 2 situations that the value will not exist because it's oscillating between 2 different values, like a sine or a cosine wave, right? If we talked about the limit as x approached infinity, it would just oscillate in between -1 and 1. So the limit as we approach negative infinity in this case does not exist, and that was because it was oscillating between 2 values. Okay. This guy over here, you can see that the limit as we approach infinity, it is crossing over and over and over again the x-axis, but hopefully you can also see that it's getting closer and closer to the x-axis. And in this case, we could actually say that the limit as we approach infinity is getting closer and closer to 0. And that also debunks the idea that you cannot cross over an asymptote, because there really is an asymptote here. It's getting closer and closer to that asymptote over time. All right, y'all. Hope this made sense. Good luck.